All right, good morning. My name is David Anderson. I'm a technology manager in the Office of Vehicle Technologies here at DOE, and I'm going to talk to you today about energy efficient mobility systems. So this is a new program that VTO is kicking off, and it really represents a change in the way we do things. You see, although we've been successful in the past supporting research, developing advanced batteries, advanced motors, new combustion engines, lightweight materials, and other vehicle and component level technologies, we're starting to change our focus. We're trying to think more broadly and consider the transportation network as a system, understanding the mobility system at large, how it's changing, and how that impacts the traditional R&D role that we've played in VTO. So I'm going to start a little bit with our motivation. What motivates us? Well, we're motivated by what we see as a massive wave of change approaching, a wave that's made up of the convergence of trends that we think are going to have enormous impacts on our transportation system in the future. So what are some of these trends? Well, it's the trend of increased population and increased congestion on our nation's highways. It's the coming reality of autonomous driving, not just the low-speed Google car or the Tesla autopilot experiment, but higher and higher levels of automation coming to more and more mainstream vehicles. It's the trend of connectivity, not just among vehicles, but between vehicles and infrastructure, and the realm of possibilities that that opens up in terms of communication and controls. It's the trend of how we view mobility as a service rather than as a car that you own, and the impacts that technologies such as GPS, mapping, and even online shopping have to our transportation network. It's the trend towards urbanization, movement towards and growth in our population centers and cities. And finally, it's the trend of big data and the ability to manipulate it both onboard and off-board the vehicle in real time. And if you ever spent time on the coast, you understand that waves represent both opportunities and challenges. If you're a surfer, you harness the power of that wave to your advantage so that you can drive towards your intended outcome. And in our case, that outcome would be one in which mobility is enhanced for all, while energy consumption, cost, and greenhouse gas emissions are decreased. Of course, there are a lot of challenges, and they're not just technical in nature, but there are policy questions, regulatory requirements, even consumer choice. It's not going to be easy, but if we don't do it right, we get pummeled by the wave, and we end up with a suboptimal transportation network that diminishes the mobility experience for everyone, and it consumes a lot of our energy resources. And so we're hoping to avoid that. Some of the mega trends that we believe are going to impact our transportation network are shown here. Population, specifically population growth. Our nation's population centers are already extremely crowded, and we spend hours of time and billions of dollars being stuck in congestion. Our population is also aging, and people are living longer. This represents a segment of the population that has not only a desire, but a real need for critical mobility services. At the other end of the spectrum, millennials are becoming more influential. These are people who have grown up and been connected to the internet pretty much their whole life, and it shapes their behavior. They're becoming used to paying for rides rather than car payments. They buy cars and drive cars less than Gen Xers such as myself, or baby boomers such as some of you out there. And they're looking for choice in how they get around. Tomorrow is election day, and income inequality has been a hot topic of conversation during this year. So why is that relevant? It turns out transportation is the second largest expense for U.S. households, only behind housing. It's even ahead of food, if that gives you any indication of its importance and its necessity to U.S. consumers. Mobility equals economic opportunity, and folks are looking for cost-effective modes of transportation that still provide timeliness and ease of use. Globally, energy demand is way up, driven not only by our economy here in the U.S., but by economies in China, India, and the Middle East. And this could have disastrous impacts to our planet in terms of climate change and resource scarcity if we don't figure out how to provide these increasing energy services without the requisite or the corresponding increase in energy resources. And finally, there's the trend of constant technological breakthroughs. Moore's law, computing power that increases to the point where supercomputers of 20 years ago fits into your pocket today. Ever increasing communication speeds that transfer data at speeds unimaginable just a few years ago. Inexpensive data storage and sensors, all of which create incredible possibilities for our vehicles and our transportation network, no matter what it might look like in the future. Industry has recognized this. Not a day goes by that we don't read in a newspaper or a magazine about an OEM partnering with an autonomous technology provider, or a transportation network company such as Uber or Lyft partnering with a car company to demonstrate what's next in mobility. Class 8 trucks carrying beer autonomously long distances across our nation's highways. Even new entrants to the space introducing what they see as mobility solutions for the future. I think it's pretty evident that there is a fundamental disruption approaching in our transportation system. And so the question is, so what? Why do we care here at the Department of Energy? Well, as a nation, we've committed to an 80% decarbonization goal economy-wide by 2050, and transportation has to be part of this decarbonization. As of this year, the transportation sector is the highest emitting sector in terms of CO2 in our economy, and so we have to be part of the solution. Turns out that transportation is often harder and more costly to decarbonize than some of the other sectors, and we might not be able to do it with just vehicles and components alone. The disruption, the market discontinuity that I just spoke about in the last slide might be the opportunity that we need to decarbonize our transportation sector. Realizing we're at the precipice of a potential sea change in our mobility system, it's our mission to understand what the energy impacts are of these coming changes and of future mobility. And so this is why we've launched this new initiative called Energy Efficient Mobility Systems. The whole point here is to identify and explore untapped transportation system level efficiencies beyond and complementary to the Vehicle Technologies Office program goals in a way that will accelerate sustainable transportation. As I said earlier, this represents a transition in how VTO operates. Traditionally, we've been focused on component and vehicle level efficiencies, and our purview has somewhat stopped there. We've looked at vehicles not quite in a vacuum, but we've looked at them independently and unconnected. And the assumptions that we've made in our research have been subject to the decisions of consumers and their behavior. For example, we have all sorts of research targets that are aligned with our organizational silos, but these targets assume a transportation system like we have today. It may not make sense in a future in which mobility is considered a service, vehicles and powertrains look a lot different than they do now, and business models completely change the utilization and drive cycles encountered by our vehicles. So we're shifting to a system level focus beyond that of our traditional vehicle level. We'll consider a network that is connected and automated, where mobility agents act in concert with one another to facilitate transport across nodes, and we'll learn how we can influence and manage consumer behaviors rather than be governed by them. You can see the Smart Mobility logo there, and Smart Mobility is really the first project that we've kicked off under the Energy Efficient Mobility Systems umbrella. Smart Mobility is actually an acronym. We are a government program, and so we have to have an acronym. And SMART stands for Systems and Modeling for Accelerated Research in Transportation. We've divided it into 5 pillars of research, as you see around the circle on the left side there. Multimodal transport, vehicles and infrastructure, mobility decision science, urban sciences, and connectivity and automation. We've assembled a consortium consisting of our national labs to tackle these 5 areas and to really try to bring science to the conversation. There are a lot of companies, both old and new, that are talking about future mobility, but right now that's really all it is talk. There's no data. And so we're trying to source data when it's available, but also to create the models and tools required to start answering questions about the energy implications of future mobility. We hope to not only understand what the energy impacts are of future mobility systems, but also to identify R&D areas that are suitable for DOE to invest in. I'll briefly cover these 5 pillars now. In the urban science pillar, we're integrating traditional transportation research practices with the growing reality that transportation in our cities is becoming more and more integrated and connected with the electric grid, with buildings, with water, with other systems. And so we're looking at solutions which are greater than the sum of their individual parts. We're going to answer questions like those that you see there. And the tools that we create and the data that we generate will be used to analyze future urban mobility systems to inform local policy decision making related to transportation. In the mobility decision science pillar, we're working to understand individual and market behaviors, not just how people decide what mode of transport to take to work today, but what vehicle to buy or to not buy 3 years from now. The questions that we're tackling here are important because understanding the interplay between consumer behavior, future technology availability, and policy drivers is a new area for us, but it's intrinsically related to our VTO program goals. In the vehicles and advanced infrastructure pillar, we're taking a holistic look at the array of both conventional and alt-fueled vehicles of the future and trying to make more informed infrastructure decisions. The obvious example here is electric vehicle charging infrastructure. We want to avoid making the assumption that charging stations in the future must follow the model of conventional fueling stations on every corner that we have today. We're driving towards informed infrastructure investments that increase consumer adoption and ROI. The fourth pillar is multimodal transport. This pillar is not only important for moving people, but also moving goods and freight, especially as the on-demand economy of purchasing goods through online retailers continues to grow, with the associated growth in freight energy consumption. We intend to understand and re-envision intermodal freight logistics, including the last mile of the delivery system. And finally, connected and autonomous vehicles is the pillar at which, at least to this point, we've done the most work. The thinking here is to quantify the energy impact of various connected and automated vehicle technologies across multiple scales and in different scenarios, and identify the opportunities that arise for powertrain electrification, lightweighting, vehicle optimization, and vehicle utilization. Some of the examples of what we're looking at here include platooning. You'll notice the picture at the top right of the slide there, which shows 2 Class 8 line haul trucks, which happen to be outfitted with specific platooning software and controls, which we tested in track environments at different speeds and different separation gaps. And we noticed an overall team fuel savings of 6% across the 2 trucks. We also noticed some thermal management impacts on the trailing truck due to the lack of airflow through its radiator. And so that's the type of research opportunity that we're trying to elucidate through this effort. We're also working with the University of Michigan, who has worked with the Department of Transportation on a safety pilot model demonstration in Ann Arbor, Michigan. We're leveraging that work, which was previously focused on safety, in order to understand the energy impacts. So those are the 5 pillars that we're tackling through the Smart Mobility initiative. And we're just getting started. We really kicked this off at the beginning of the fiscal year, just over a month ago. But we have done some preliminary research to start addressing some of the questions in my previous slide. So I'd like to give you a preview of some of the results of that previous analysis. I was hoping to say this is hot off the presses. Turns out, as of today, it's still at the presses. So it hasn't been released yet. You're getting an early look of some of these analysis results. So first, a team led by Argonne National Lab and the National Renewable Energy Lab looked at the upper and lower bounds of per vehicle fuel consumption across several scenarios. A conventional baseline case, a case where you have partially automated vehicles, a case where you have fully automated no rideshare vehicles, so that's fully automated taxis or robocabs, and then fully automated rideshare taxis. And what we see, not surprisingly, is that drive cycle smoothing, shown here in the pink bars, have a potential to reduce fuel consumption being shown on the x-axis. And we'll talk about what drive cycle smoothing is in just a minute. But the benefits are dominated by these green bars here, which represent right sizing, vehicle right sizing, which means vehicle mass reduction and the associated powertrain downsizing requirements. So how might we achieve vehicle right sizing? Well, you might know vehicle performance, at least as measured by acceleration, has improved pretty steadily since the early 80s, when it took about 14 seconds to go 0 to 60. Now we're under 9 seconds to do the same thing. So the question must be asked, in a future in which vehicles are autonomous, can this performance metric be relaxed, or do we still have to have such fast acceleration? Also, quite a bit of mass of our vehicles today is devoted to passive safety, about 120 kilograms as of 2010 model year vehicles. So we have to ask the question, in a future in which accidents are rare and avoidable due to automation, can we remove some of this mass, which leads to further powertrain downsizing? So I mentioned drive cycle smoothing a minute ago. So what is drive cycle smoothing? It effectively means smoother acceleration, smoother braking, even removal of stops on a trip. A team at Argonne National Lab has looked at how drive cycle smoothing through automation might impact vehicles of 3 different powertrain types: conventional vehicles, hybrid electric vehicles, and battery electric vehicles, with increasing levels of automation represented by the different colors. And what they have found is that for all 3 vehicle types, there's the opportunity to save energy through drive cycle smoothing. It's not surprising that the overall savings for conventional vehicles are probably greater than the others. Well, that's because conventional vehicles are already less efficient than hybrids or battery electric, so there's more fuel to be saved there. So it's pretty obvious to state that less aggressive driving will result in fuel saving. So let's look at a simple example of how that might be implemented in the real world. Some of our researchers at Oak Ridge National Lab have put this example together, and consider this scenario where you have 2 lanes or 2 roads merging, and vehicles driving along the primary lane represented by the blue dots, vehicles driving in the merging lane represented by the red dots. And in the baseline case, the vehicles in the merging lane must stop and wait before proceeding behind the vehicles in the primary lane, and the associated fuel usage during idling. Well, in a case where we have vehicle coordination enabled through connectivity and automation, the vehicles in the merging lane can merge much like a zipper with the vehicles in the primary lane, with only minute adjustments in vehicle speed. The team at Oak Ridge has done some analysis to look at what the benefits of this are, and have found that you could have up to a 50% reduction in fuel consumption, average fuel consumption for the fleet of vehicles in this example, while at the same time reducing average travel time by 7%, illustrating that there doesn't have to be a trade-off between efficiency and speed. So let's look beyond per vehicle fuel consumption at total vehicle miles traveled, or VMT. We expect the potential for increased VMT across all of the scenarios I described earlier, and in the fully automated case, it could be significant. I'll pull your attention to the light blue bars here. That represents previously underserved groups, folks that previously did not have mobility options that could be brought into the transportation system. Up to 30% of the increase in vehicle miles traveled could be due to new consumers. But that's dominated by these red bars here, which represent easier travel. If your time cost of travel is reduced, if you can be productive while riding along in your autonomous vehicle, it could induce a tremendous amount more of entrance into the transportation system, significantly increasing vehicle miles traveled. Notably, the little green bar there represents savings due to ride sharing, and it's not insignificant, but it doesn't really counteract the other increases that are likely. So repeating my earlier statement, what does this all mean? Well, it means there are dramatic implications for energy in our climate system. If we take just some of these preliminary analyses and add them together, what do we see? Well, we see that given the range of potential outcomes for future mobility scenarios, it's possible that transportation energy consumption could increase by up to 200%. On the other end of the spectrum, if we are able to use connectivity and automation to maximize every possible efficiency in our vehicles and avoid any and all negative rebound effects, we could reduce energy consumption in the transportation sector by up to 90%. And so we throw a party, we pat ourselves on the back for bounding the problem so well. I don't think this chart is very instructive or informative, other than to point out that the range of uncertainty is pretty great, and there's more research required. So, as we study this range of implications, we're also trying to determine, as I said before, what DOE's R&D role could be. We're still working on the analysis, but we're trying to figure out what we can invest in order to drive towards that negative 90% that I mentioned earlier. And some of these are shown here. Well, one Big data, the ability to source and use data in real time on board the vehicle to not only control the vehicle control system, but also the transportation network control system. Vehicle design. Our vehicles today are designed around a 20th century transportation network. 21st century mobility system might result in vehicles that look a lot different than they do today and provide opportunities for improvements through lightweighting and powertrain optimization. Connectivity and automation will only be enabled through advanced sensors which have to be created and other devices, not only for vehicles, but for travelers too and the infrastructure around them. And finally, artificial intelligence and machine learning. It would be a fallacy to think that autonomous driving will be enabled through traditional computing approaches like we have today. Companies such as IBM, Intel, and NVIDIA are already working on advanced computing approaches using AI and devices that learn over time. And this is really a new area of research that I think will be really impactful to mobility in the future. So to wrap up, I'm going to pose a question, one that we've been asking ourselves in VTO lately, and it's, what will future mobility look like? It's difficult to predict the future. I like to think back to Orville and Wilbur Wright, who in 1903 made man's first powered flight in Kitty Hawk, North Carolina. That was 1903. And I'm sure they could not predict that 66 years later, less than a lifetime later, we would put a man on the moon. And I'm sure they couldn't envision or predict air travel as we know it today. 8 million people flying around the planet in jet-powered aircraft. So it's difficult to predict the future, but we can think about future scenarios, such as these. So a conventional baseline, this is really business as usual. In this case, we remain on a similar trajectory to the one we're on today, with increasing efficiency gains in our vehicles, somewhat counterbalancing the increases in population growth and mobility. It could be that Electric Avenue is in our future. This is one in which electric drive technology breakthroughs expand low-cost, low-carbon options for both personal and freight mobility, and it's combined with connectivity, automation, and integration with the electric grid. A right-sized evolution might depend on automation providing us with a collision-free future, allowing for a radical redesign of vehicles and powertrains to achieve radical energy savings while making multimodal transport realizable for the masses. A dystopian view might lead to ultimate cyber sprawl, where everything and everybody is constantly on the move and people expect instant responses to their on-demand or online requests. Travel and freight, or travel energy consumption would increase dramatically in this scenario. And finally, a beyond mobility scenario would combine connectivity and automation with other emerging technologies such as consumer 3D printing, which would nearly obviate the whole need for mobility altogether. Now, granted, that one and some of the others probably sound a bit fanciful, but I would refer you back to Orville and Wilbur, to whom space travel probably seemed a bit fanciful as well. So that's where we are right now with energy-efficient mobility systems and smart mobility. Like I said, it's a new area for the Vehicle Technologies Office, and we're just beginning work to understand how vehicle and transportation energy consumption will be impacted by the coming transformation we see in mobility. We're also working to understand and make sure that energy is represented at the table right along with mobility and safety. My overall message is simple. Our transportation network is evolving perhaps more quickly than we had imagined. And so the Vehicle Technologies Office must evolve as well. Given transportation's place in our global energy system, it's imperative that we work to ensure that however people move around in the future, however goods and freight are moved around in the future, and whatever the modes and vehicles are that provide this mobility, we work to ensure that the system is sustainable for the long term. Thank you for your time.